Hi, I'm Philip Bille. Welcome to this video on the weighted quick union data structure. The weighted quick union data structure is a simple extension of the quick union data structure. We now maintain an additional array of length n that stores the size of the subtree rooted at node I. So we implement the operations as follows. The init is the same as before, except that we now also initialize this size array. The find operation is exactly the same as before. The interesting change is now the union operation. Here we now always take the smaller of the two trees and make it the child of the root of the larger tree. So for instance, if we have two trees here and we want to do a union on an element in one tree and an element in the other tree, then how do we connect these two trees? We always take the smaller tree and make it the child of the root of the larger tree, as illustrated here on the right hand side. So this of course affects the sizes of the subtree, namely the size of this guy here. So we also update the size array to say that, well, the size of this node here is now the number of elements in this subtree plus the number of elements of the smaller tree. And the intuition here is that if we use this strategy, always taking the smaller tree and making it the child of the root of the larger tree, then we roughly balance the trees, producing trees of low depth. So let's see an example of the weighted quick union data structure. We start by saying init9 just as before, and that produces 9 tiny trees. We're going to implement the same operation as before, so now we do a union 3.2. So we combine these two small trees. They now have the same size, so we just arbitrarily connect one of them to the other. So in this case we do as before and connect to tree like this. We then do another union operation, so union 2.7 again. Now the interesting part happens, right? Because now we're in the situation where, so union 2, that corresponds to this tree here, union 7 corresponds to this tree. This tree is the larger tree, so we should connect 7 to the root of 3 as we do here. Okay. Next operation is a union 5.4. Again, these have size 1, so we just connect them, say like this. Union 8.3. So now we have this tree here, and we have this tree here. This is the larger tree, so 8 should become a child of 3, like this. We do union 1.0, two trees of size 1, so we just combine them like this. Union 6.1, so now we want to combine this tree with this tree. This one is the larger, so 6 becomes the child of 1. Union 7.3. These are in the same tree, so nothing happens. Union 5.1. We have that here is 5 and here is 1. This is the larger tree, so to connect 5 and make it a child of 1. Union 6.3. This should be the last operation. We have that there are, so we want to connect this tree because 6 is here with this tree containing 3, and there are let's see, there are 5 elements in this tree and there are 4 elements in this tree. So we connected the smaller one to the larger one like so. And if you compare this to the previous quick union operation, you see that this tree is much more balanced than before, so the depth is smaller, and here indeed the maximum depth is only 2 of this tree. Here is the pseudocode for the new union operation. Notice that we need to do a little more work to maintain and update the array, storing the size. How fast is this operation? As before, the time is order d, where d is the depth of the tree. But what is this depth of the tree? Let's try and analyze that. So let's show that the weighted quick union always produces trees where the depth of the trees is at most log n. To see this, consider a node I with depth di. Initially, when we do the init operations, di is 0. Now, di can increase by 1 only when the tree is combined with a larger tree, as shown over here in this example. Right, we have I here in a small tree, and when we combine it with a tree that is larger, then we add this edge here, effectively adding 1 to the depth. If I is in the side of a larger tree, so if I is somewhere over here, then nothing happens to the depth. So the resulting tree that we get after increasing the depth of I by 1 must be at least twice the size of the original tree. So each time di increases by 1, the size of the tree containing I doubles. We can at most double log n times, and hence di can be at most log n, which is what we wanted to show. So now we know that we have a solution to the union find problem that uses order n time for init, order log n time for union, and order log n time for find. Summing up, these are the 3 data structures we've seen for union find problem. And of course, the challenge is, can we do even better?